Okay, this is the first of three videos that deal with the alkane chapter. And let's just look at a few fundamental things about alkanes. What are they? Okay, first let's start with a key definition here, and this is hydrocarbon. Okay, so I need to turn this into a pen, sorry. Okay, so what is a hydrocarbon? Hydrocarbon is a compound composed only of carbon and hydrogen. Okay, if you look at how this course is organized and look at the titles of the chapters, you can see that it's organized by something called the functional group approach. A functional group is a small grouping of atoms or a structural feature that leads to a characteristic reactivity pattern. And you can see the jacket of the book for a list of common functional groups. Let me just illustrate that. Let's see. Many of the later chapters in this course are concerned with compounds that have a carbon-oxygen double bond. And that's a good example of a functional group. The carbon-oxygen double bond has a characteristic reactivity pattern. Okay, in Chem 313, we're going to cover all of the hydrocarbon functional groups, and these include alkanes. And alkanes are characterized by the fact that they don't have any multiple bonds in the structure. They have only single bonds and no multiple bonds, and they contain only carbon and hydrogen. Alkenes, or olefins, contain a carbon-carbon double bond. That's a later chapter in the book. Alkynes will contain a carbon-carbon triple bond, and aromatics will contain a benzene ring. Okay, and that's the last chapter in Chemistry 313. Okay, alkanes, we say, are the least reactive of all functional groups, and sometimes we use the term unfunctionalized to refer to alkanes because there's no particular reactivity associated with the alkane grouping. This is the only chapter where there's going to be no detailed discussion of reactions. The only reaction we're going to discuss in detail is combustion, and that's because it can relate to key principles of relative energetics of molecules, and we're going to use combustion to tell us a lot or to compare the energies of molecules. But we're not really going to study the combustion reaction in detail. Okay? An alkane that doesn't have any cyclic components is characterized by having the formula CnH2n plus 2. And you cannot possibly have any more hydrogens per carbon atom than you have in an alkane. Thus, alkanes also have other synonyms. They're commonly called saturated hydrocarbons. We've crammed as much hydrogen per carbon as we can possibly get into the molecule in the alkane structure. Okay, another synonym is the paraffins. Okay, all right, so let's look at some structural issues associated with hydrocarbons and with organic compounds in general. How do we account for the tetrahedral geometry of methane, shown here, the simplest organic compound? Okay, so first we need to think about a few fundamentals of valence bond theory. That's going to be our predominant way of looking at organic compounds. All right, so here is the s orbital, which is the only orbital that hydrogen has. And notice that one of them I didn't color in. I will call this unshaded. And this the shaded portion. Okay, so to make a bond, what we have to do is we have to overlap orbitals of like phases. Okay, so for example, if we took two unshaded or two shaded orbitals, okay, we would refer to either of these as being bonding interactions. And if we took two orbitals that have different phases, we would call this situation antibonding. And this is the way we don't want to put these together. This is actually higher in energy than if we never had any interaction at all. Okay, so antibonding is bad, bonding is good. All right, carbon has s and p orbitals in the valence shell, in the second shell. This is the ground state configuration of a carbon atom. This is what a carbon atom looks like. The s orbitals are lower in energy than the p orbitals. So the electrons prefer to congregate in the s orbitals, and then we start filling the p orbitals. This leaves us only two unpaired electrons that we can really use for making more bonds. So in the ground state configuration of the carbon atom, it looks like only two bonds could ever form. Okay? Now, the thing to note here is that this is the ground state configuration of the carbon atom. However, the carbons we're going to be concerned with are carbons that are parts of molecules. So this doesn't necessarily apply. Okay. All right, so let's look at how we can create more bonding sites. One thing we can do is we can promote an electron from one of the s electrons and promote it to the empty p orbital. Okay, and this would give us this configuration right down here that would allow us to now make 4 bonds. But when we think about what do p orbitals look like, we realize there's a problem here. So p orbitals look like this. They have a dumbbell shape, okay, and each end of the dumbbell has opposite phases, okay? Their orientation is along the Cartesian axis. So we have a py orbital, a px orbital, and a pz orbital, depending on which axis it aligns on, okay? And here, I'm not really drawing this. It's very hard to draw stereochemistry in an orbital. So just take this as the best I could do. So hard to project stereochemistry in an orbital. Okay, so we're used to seeing it in a bond. All right. All right, so we can make 4 bonds from this configuration down here that's circled, but look at how the p orbitals orient. They orient on the Cartesian axis. They're at 90 degrees to each other. Okay, but that's a real problem for the tetrahedron because our bond angles here are not 90 degrees. They're 109.5 degrees. All right, so what do we do here to solve this problem? What we do is we mix the s and p orbitals into 4 identical orbitals, which we call sp3 hybrid orbitals, okay? Each sp3 hybrid is 25% s and 75% p, okay? Now we can make bonds that are equal to each other in their bond angles from the sp3 orbitals. All right. Let's take a look at what does an sp hybrid orbital look like. It doesn't matter what this number x is. Sometimes x is 1, 2, or 3, and when it's 1, we typically don't actually say sp1, we just say sp. All right, so imagine that we are taking an orbital Okay, it's shaded and unshaded, and pairing it with an S, which all has one phase. And what we'll see here is that because the unshaded and the shaded cancel, okay, they subtract from each other. That means the backside or the left side of this orbital gets smaller, okay, and on the right side they add together, okay? They're adding together because they're of like phase, so the right side gets larger, okay? All right, so this is a really advantageous situation to have to make a bond. So the sp(x) orbitals are really good for engaging in a certain type of bond called a sigma bond, which is basically direct or head-on overlap. Okay? All right, so we can form an we can form a very strong sigma bond by taking an sp hybrid orbital and an s orbital at hydrogen. This is how we make the bonds to hydrogen, or to any other heavier atom. We would bond two different sp hybrid orbitals together, like you see in this lower structure right here. Okay, all right, so this is a sigma bond. This is one type of bonding. The other type of bonding we commonly see in organic chemistry is called a pi bond, and this involves purely p orbitals, okay? And a pi bond comes about through side-on overlap, okay? All right, so bond strength is kind of determined by the degree of overlap, and what you can see with the pi bond is that they don't really point at each other, so we have a weaker bond. There's two different bonding contacts, but their degree of overlap altogether is not quite as strong. Okay, so in general, sigma bonds are stronger than pi bonds, and in organic chemistry, only a pure p orbital can make a pi bond. All right, so here's an important relationship. Sorry, I partly covered it, but in organic chemistry, sigma bonds result from overlap of sp hybrid orbitals, or S if hydrogen's involved, while pi bonds result from overlaps of p orbitals. Okay? All right, and that's an important generalization to remember. All right, so let's look at some actual structures here. Here is methane on the left. I drew the ones that come in and out of the board as projections because, again, it's hard to give stereochemistry to an orbital. But we have 4 equal CH bonds, each made by the overlap of an sp3 at carbon with an S at hydrogen. Okay? The molecule over to the right is called ethane. It's the second simplest organic compound, C2H6. It contains 2 carbons, and our CH bonds are made up exactly the same way they're made up in methane over to the left, but the CC bond results from overlap of an sp3 orbital at one carbon with an sp3 orbital at another carbon. Okay, both of these molecules are tetrahedral, and this is an association that is pretty valid. We're going to associate tetrahedral geometry with sp3 hybridization. All right, so sp3 is not the only game in town. We don't have to involve all of the p orbitals in the hybridization scheme. All right, so another geometry that we commonly see in organic chemistry is trigonal planar geometry, and we're going to associate this with sp2 hybridization. First, we're going to look at an inorganic molecule, borane, BH3. All right, so boron, this is the configuration of a boron atom. It looks like there's only one electron available to make a bond, but this is BH3, so what we would do is promote one of the S's over to a P. This gives us an S and two P's, and now we're going to hybridize the orbitals that have electrons in them and leave the orbital that's empty out of the hybridization scheme. So this gives us three sp2 orbitals. These three are all equal to each other, and the p orbital. Okay, so we make the sigma bonds with the sp hybrids. So we need three sigma bonds in BH3. Each BH bond is going to result from the sigma overlap of an sp2 orbital at boron and an s orbital at hydrogen. Okay, each of these orbitals, again, a slightly higher s character, but same general shape as an sp3 orbital. A little bit different relative size of the left and right lobe, but this is general. The same general shape applies, and this is 33% S and 67% P. All right, so each BH bond is going to result from the sigma overlap of an sp2 orbital at boron with an s orbital at hydrogen, and the empty p orbital that was left out of the hybridization scheme, it's empty, so this is our site of Lewis acidity. All right, so BH3, we're not going to achieve an octet in BH3, but this is what accounts for it being such a good Lewis acid. All right, now let's go to an organic compound, ethylene. CH2, CH2, held together by a double bond, has the molecular formula C2H4. All right, so when we use the sp2 hybridization, this allows for the three sigma bonds to engage in a planar arrangement, okay, with 120-degree bond angles. So if we look at the structure down here, these are our three sigma bonds, the ones that I've designated with a check mark, okay? The p orbital at sp2 carbon is now going to have an extra electron in it. So instead of being empty like it was in BH3, okay, because there's one more electron at carbon right here, this means that we are going to have an electron still left, okay? So this is now adjacent to the other carbon having the same configuration, and we've set it up so beautifully that we can now have a pi bond between these two carbons, okay? So these p orbitals that were left out of the hybridization scheme can now engage in pi bonding, okay? All right, so net result here is that the CC double bond that we see in ethylene can be described as a sigma bond for one of the bonds and a pi bond for the other bond, okay? All right, now another thing here. I've drawn like two contacts here between each side of the p orbitals. Remember, this is just one pi bond, even though it has two contact things like that. So don't let that confuse you. Don't let that imply that there's an extra bond, okay? The pi bond has to have the contact on each side like that, okay? All right, let's go to linear geometry, and this is sp hybridization or acetylene, which has the empirical formula C2H2. All right, so here's what's going to happen in acetylene. We're going to leave two of the p orbitals out of the hybridization scheme, as you see here. So when we promote and hybridize, we're going to get two sps and two purely p orbitals that were left alone. Each of these sps is 50% s and 50% p. Okay, So the sp hybridization scheme gives us 2 sigma bonds, okay, at each carbon. That carbon right there has a sigma bond by the check mark, and the other carbon has the equivalent sigma bond going to it. Okay? So the p orbitals that were left out of the hybridization scheme can now engage in pi bonding as well. Okay, so there is a pi bond for those that are overlapping the way pi bonds are supposed to, and here is another pi bond right here. All right, this one's going to go behind that one, but each of these pi bonds results from a pi overlap on each side of the p orbitals. Okay? So this forms via overlap of an sp orbital carbon with an s orbital hydrogen for the CH bond, and the sigma bond forms via overlap of 2 sp orbitals from each of the carbon atoms. All right, so the triple bond, what does it consist of? It consists of 1 sigma bond and 2 pi bonds. Okay, and forever and ever, we need to now just form this tight association between linear geometry and sp hybridization. All right, so here's a table that we've seen before. I think I showed it in chapter 1. What happens to bond length and bond energy as the degree of bonding increases? Okay, so again, the CC bond length decreases as the bonding becomes, or as the degree of bonding increases. 1.54 for the single, 1.34 for the double, 1.2 angstroms for the triple bond. Okay, the bond association energy increases, and 375 times 2 is 750. Our bond energy here isn't twice as great, and this is because the pi bond is weaker. Okay, I don't know why that happened. Weaker than the sigma bond. I think I didn't lift it high enough off the table. Okay, all right, so the pi bond is weaker than the sigma bond in this case, and that's why it's not twice as strong. All right, now another situation, as percent S character increases, bond strength increases, and consequently bond length decreases. Decreases. Okay, so the CH bonds, let's look at the effect here. This is hydrogen at sp3 bound to an sp3 orbital at carbons, 1.11. A little shorter when it's bound to an sp2, and shorter even when it's bound to an sp3. Okay? Sorry, to an sp. All right, and the CH bond association energy is increasing as the percent S character at carbon is increasing. Okay, so it goes from 421 for hydrogen at sp3 carbon to 547 for hydrogen at sp carbon. sp is 50% S, sp3 is only 25% S. So this is an important relationship to remember. Okay, and this is bond association energy. Remember, we defined it in the previous chapter, but it's the delta H for breaking the bond. Okay, so let's do a couple problems here. Which is the better structure for allene, A or B? And explain your answer choice. Okay, you should pause the video, do this yourself, but I'm going to go right into the answer. Okay, so the important thing to remember, let's look at each carbon. This is sp2 and trigonal. That's also sp2 and trigonal. But this middle one is sp and linear. Okay, so let's focus on the middle carbon. Okay, and again I have to draw orbitals with a stereochemical projection. Okay, so let's shade that one, shade this one. So that's our middle carbon right there. Okay, this is an sp. It's going to have 2 p orbitals. All right, so we want to now think about how these p orbitals engage with the bonds to the outer carbons. Okay, so the one on the left has to overlap like this. All right, so that's the one that goes straight up and down. Okay, let's shade it so that they have the right shading. So there's our bond on the left side. All right, now on the right side, we have to also have it overlap the same way. Okay, so this is now the side-on p orbital. We'll call it, I guess, the pz orbital. So if it bonds that way, that means the hydrogens are bonded this way. So we should choose the structure where the outer carbons are have opposite orientations for their planes. So we should choose the one where the left carbon has the plane of the board and the right one, or actually it would be the opposite here. Sorry about that. Okay, so we're going to choose the one where the planes are perpendicular to each other. One plane, or one of the planar carbons, trigonal planar ones. This is in the board or in the screen, and this one is actually 90 degrees to the screen. So we should pick B as our answer. C is linear and thus SP, and there's another repeated structure using the chemical drawing program shown there. The central carbon has 2 p orbitals at 90-degree bond angles, and they're each available to make pi bonds, but you can't make more than one pi bond from each of the p orbitals. So you're going to end up with this structure where the outer carbons are in opposite planes. Okay, or not in the same plane. Okay. All right. All right, how many pi bonds are present in the compound depicted below? Okay, so how do we do that? Well, we know that we don't really focus on the sp3 carbons. It's only the trigonal and the linear carbons that are going to give us pi bonds, right? So we only need to focus on the multiple bonds, or carbons that are either linear or trigonal planar. Okay, so those are the carbons that are going to give us our pi bonds. All right, there's 2 in an alkyne, or in the carbon-carbon triple bond. It's 1 sigma and 2 pi. There's 1 there. 2 plus 2 plus 1 plus 1 equals 6. There are 6 pi bonds. The double bonds consist of a sigma and a pi bond, and the triple bonds consist of a sigma bond and 2 pi bonds, and we add all the pi bonds together. We come up with the number 6. All right, this will be the last slide here, but a more comprehensive way to look at bonding is molecular orbital theory. The previous description we gave was known as valence bond description, which considers each carbon and hydrogen as isolated entities. But when they're combined in the same molecule, the interactions are a little bit greater than that. But what we're going to see here is that we can get a more accurate description through molecular orbital theory, but most of the systems that consist of single bonds, the valence bond theory is going to work just fine. The only place we're going to see where it breaks down here is when we have multiple pi bonds in our compounds in chapters 10 and 11. And these can only be described by molecular orbital theory. All right, so I'm just going to draw the molecular orbital diagram of the hydrogen atom just so that we understand the fundamentals of molecular orbital theory. All right, so outside of the diagram, we have the atomic orbitals are in magenta. Okay, so these are the atomic orbitals right here. All right, so we have two of them. Okay, we have to have the same number of atomic orbitals and molecular orbitals. So that means that we're going to have two molecular orbitals as well. And these are the orbitals in blue. These are in the middle of the diagram. Okay. All right, so the magenta is before these hydrogens find each other, and the blue is after they find each other, the energy diagram. Okay, we're going to combine them in two possible ways. We're going to combine them in a bonding interaction where we combine the like phases, and this is good. The energy is lower than the free atoms. Okay, if we look at the net stabilization, it's just how much lower in energy are the electrons after we make the molecular orbitals than they were before. Okay? All right, so it's really the energy of the bonding orbital, difference between the bonding orbital and what we call the energy of non-bonding. This is the energy of hydrogens that never found each other. Okay. All right. Even higher in energy than the non-bonding atomic orbitals is this antibonding orbital right here, and the antibody bonding orbital usually has the asterisk, okay, or the star means antibonding. Okay. All right, so the antibonding is actually much worse than if the hydrogen atoms had never gotten together in the first place. All right, this final number here is called the bond order. This is the degree of bonding, and this is a relatively simple equation. Number of electrons in bonding minus the number of electrons in antibonding. Okay, so to work this equation out, it's 2 minus 0 divided by 2. This equals 1, and this describes a single bond. Okay. Okay, so the bond order in H2 is 1. All right, so what can we see from this orbital diagram? Okay, let's just ask a fundamental question. Why don't we have helium-2 making a bond compound totally analogous to H2? Well, there'd be 2 more electrons here, right? And if we did this, the bond order would be 0 because the number of electrons in bonding and antibonding orbitals would be 0. So there would be no bond. Okay, so helium-2 would not exist because our bond order is 0. All right, so let's just remember the fundamental of molecular orbital theory for a while, and I don't think it's going to come into play until chapter 10, but it's an important concept. Okay, so that's where this video stops, and the next one will begin by looking at nomenclature issues for alkanes.